Hello everyone, this is lecture 32 for the quantum mechanics. In the last lecture, we were studying about the potential barrier and we have completed the step potential also. So, today we'll see the infinite square well potential. So, how it is different means in the step potential, we have seen just a step of potential. In the barrier, we have seen the barrier of potential. Now, there is this potential and there is some well inside it. So, this is called the infinite square well potential. So, that's how it is defined. There is infinite potential in the both sides, and the middle of it, there is a zero potential. So it can be of two types, means asymmetric and symmetric. So asymmetric means you will define it like 0 to a, and for the symmetric cases you will define it like 0 here and minus a by 2 to a by 2. But there will be this well will remain same. So these are the two conditions, so we'll study them separately. So in the asymmetric case, for x less than 0, there will be infinite potential, and for x greater than a, there will be infinite potential, and between 0 to a, there will be 0 potential. Same for the symmetric case. For the minus a by 2 less than minus a by 2, it will be infinite potential. Greater than a by 2, infinite potential. And between minus a by 2, it will be 0 potential. So we'll first study the asymmetric case. So, when we study, means there is, let's assume there is this potential. And there is this particle having energy E. So it will lie somewhere here. So classically, it will have some momentum. And momentum can be find it because there is no potential. So there will be only kinetic energy. So momentum will be under root 2 me plus minus because it is going to and fro because of this potential barriers. So that's why it will go to and fro motion here. So momentum will be plus minus 2 me classically. But how can we write the equations for this particle quantum mechanically? So for that we know the procedure. First we need to write the Hamiltonian. So what is the Hamiltonian? That is the total energy. So it is kinetic energy plus potential energy operator. Now we need to find all the possible eigenstates and the eigenvalue. For that we need to write the eigenstate equation. That will be this: H phi x equal to E phi x, where this E is our eigenvalues and phi x are the eigenstates. So we need to find these all eigenstates and the energy eigenvalues for this particular state. Then we need to write the time independent wave equation. That will be psi x0 equal to Ci phi I x. So it will be all the eigenstate phi 1, phi 2, phi 3 and C1, C2, C3, and this is your wave equation. Now you need to write the time dependent wave equation. That will be means time evolving wave function. So this is your time independent wave function. This is your time dependent wave function. So when you have this time independent one, then you can just write the dependent one, that how the wave function is evolving. That will be this: exponential minus I h t by h cut psi x0. So this is how you will write. So this is the procedure. Let's follow the procedure. So first we need to write the Hamiltonian. So we know the potential is 0. So it will be only the kinetic energy. So it will give us this: h equal to p square by 2m plus vx. And we know what is the momentum operator, that is minus I h cut del by del x. So square will give you minus h cut square del square by del x square 2m plus vx. And now if you just operate this h on the particular eigenstate phi, then it will be h phi will give you e phi, and here also it will be del square phi by del x square plus v phi. So this will be your equation from the Schrodinger equation. So you know now why we are using phi here, and in the step potential and the barrier potential we use the psi. So at that point we have the discrete eigen means energy states. Means here in this case when it is a bound state, so we always have the discrete eigenstates or the eigenvalues. But we have when we have the unbound state, then we have the continuous eigenstates or the eigenvalues. So that's why we are having here phi, because now it is a bound state. So there will be a particular discrete eigenvalues. So that's why we are using phi here. So we will need to find the different eigenstates here. So that's why we'll use this equation. Now particle can't be present here and here or here. Why? Because the potential is infinite, so there will be zero probability of particle presenting here. So because there is no tunneling and anything can occur because the potential is infinite. So the phi will be 0 here and phi will be 0 here, and phi will be something here. Means all the eigenstates will be present inside this well. So particles should not be present in the region x greater than a or x less than a. So all eigenfunction must also be 0 in these regions. For x less than 0 and x greater than a, v will be infinite. This is the potential infinite, and the eigenstates will be 0. So but for the x 0 to a, potential means there will be no eigenstate. So we need to write this equation only for this case, x 0 to a. So for x 0 to a, what we have, the potential is 0. Here the potential is 0. So we just need to substitute the potential value here. So it will be 0 here, and the remaining equation will be this plus this. So this will go to this side, will become plus. So rearranging this, we'll get this equation: del square d square phi by dx square plus 2me by h square phi equal to 0. Now this del changes to d. Why? Because this is a complete differentiation. So only one variable is present, that's why we are using the complete differentiation d. Now we can just solve this equation as we know how to solve the differential equations. So it is a second order differential equation. So we will get here d equal to plus minus iota k. So solution will be c1 exponential I kx plus c2 exponential minus I kx. So we can just open this in the cos and sine terms: cos kx plus I sin kx, cos and minus sine. Now just separate the cos terms and the sine terms. You will get c1 plus c2 cos kx plus I c1 minus c2 sin kx. So we'll call this complete thing as A. This iota is also inside this, and this is as B. So the solution will be this. Means now we have the solution or the eigenstates. Phi x will be A sin kx plus B cos kx. But still these are not known. Means these are unknown, A and B. So we need to find them. So how can we find them? Now we'll use the boundary conditions. What are the boundary conditions? That we know that phi is 0 outside this, less than 0, and it is 0 greater than A, but it is non-zero inside because phi is the eigenstates. So we know at the boundary the wave function must be, or the eigenstate must be, continuous. So if phi is 0 here, then at x equal to 0 it must be 0, means at all these points. So at this boundary this will be continuous, means phi must be continuous. So, and also at this point x equal to a, phi must be 0. So we will use this condition. We just substitute the value of x as 0 and a, and we will use these conditions. And there is one more condition, that is d phi by dx equal to continuous. So this must be continuous, but this is not applicable here because this is the case when the potential is same. But here we will see that there is discontinuity in the potential also. There is just a potential jump from 0 to infinite. That's why we can't use this. Boundary condition is not applicable. Not applicable here. There is a discontinuous jump in the potential at x equal to 0 and x equal to a. So potential is discontinuous at x equal to 0 and x equal to a. That's why we won't use this condition. We will use only this first condition. So using this means phi must be 0 at x equal to 0. So put x equal to 0 here. This will become b and this will become 0. So b will be equal to 0. So we find here b equal to 0. So just substitute here. So the resultant will be phi x equal to a sin kx. Now at x equal to a also phi must be 0. So at x equal to a sin ka equal to 0. Now we know a can't be 0. Why? Because if a becomes 0, then this whole thing will become 0 and there will be no eigenstate present inside, but particle is still there, so a can't be 0. So sin k must be 0 and k must be n pi. So from here we will find the value of k, that is n pi by a, and substitute in this equation, and we will find this phi x equal to a equal to sine, and in place of k we will write n pi by a, so it will be n pi by a x. So these are our eigenstates, so we just find them. So we will just substitute the value n 1 2 3 4 5 and we will get the different eigenstates. Now see that it can't be 0 also, because if it will become 0, then again it will become 0. So there is no eigenstate inside. So that is not possible. That's why it will start with n equal to 1. So 1 2 3 4, and still this can't be negative also, because minus 1 minus 2 minus 3. Why it is not negative? Means not possible. Because for n equal to 1 and minus 1 you will get a sin pi x by a and minus a sin pi x by a. So see, you have two eigenstates with plus 1 and minus 1, and both are not linearly independent, but we know that eigenstates must be linearly independent. So to make them linearly independent, that's why we are having only these positive values. Now we have our eigenstates, we need to find the eigenvalues also. So we just do here square of these both sides, k square, a square, and square pi square. So in place of k square we'll substitute this value, this 2me by h square. So this will become this. Now from here we can find the value of e, and these are our eigenvalues: n square pi square h square by 2m a square. So now we have eigenvalues, we have our eigenstates. Now we can just write this. So first let's visualize that what are these eigenstates and the eigenvalues. So four different states: ground state, first excited state, and third, second. So n1 2 3 will get energy as pi square h square 2m a square, and 4 and 9. And similarly the eigenstates will be a sin pi x by l, a sin 2 pi x by l, a sin 3 pi x by l. That's how it will go. Now see, for this you can just plot it at x equal to l. You will see that it will go to sin pi. That's why it will go like this. Means this curve is up to pi. You can say at x equal to l it will go up to pi, and for x equal to l then it will go for 2 pi for the second one. So it will go like this. And for x equal to l it will go to 3 pi, means 2 pi here and this 3 pi. And similarly you can plot the other one also. So that's how you can just visualize the eigenstates, different eigenstates. Now, what is the meaning of this? Means inside the potential well, you will have these three eigenstates, or it will go continuously above. So these are discrete eigenstates in which the particle can be present. And if you normalize these wave functions, then or the eigenstates, you will get a as root 2 by a. So you know how to normalize the wave function. So that's how you will get equal to root 2 by a. So this is your discrete eigenstates. Now let's say particles present somewhere here. Then the third step is you need to write a time independent wave function. So this particle is superposition of all these states, means it will be present everywhere, and there will be probability distribution of this particle in all these states. So we need to write a time independent wave function that will be psi x0 equal to ci phi I x. So it will be sum of c1 phi 1 c2 phi 2 c3 phi 3, and then we can, if we have this one, then we can write the time dependent later, that is defined in this formula. This is the time evolution of the wave function psi xt equal to e exponential minus iota h cap t divided by h cut psi x0. Now we have completed this procedure. Now let's see for the symmetric one also. Now you have the solution for the asymmetric. So for the symmetric, you will get simply this. These are the conditions: 0 for the minus a by 2, and infinity elsewhere. This is the potential defined. Now you need to try it by yourself, that you will follow the same procedure as we did here. Okay, all the same procedure, and you will get this results. Means root 2 by a, this is the value of a after normalization, cos n pi by ax n equal to 1357. So for different n, you will get cos for the odd ones, and for the even ones you will get sine. Means here you get the this one sine for all the values, but here you will get sine and cos for odd and even. So for the odd numbers, odd states will be with cos and even states will be sine. So you need to prove this, and in the next lecture I will provide the solution. So you must try it by yourself first, only then it will be helpful. So this is the symmetric case, and these are your eigenstates, and then eigenvalue will remain same as it was in the asymmetric cases. And how to normalize? You know how to normalize for the asymmetric case: 0 to a phi n square dx. This just put it equal to 1, and you will get the value of a, that is root 2 by a. This will remain same. And for the symmetric cases, it will be minus a by 2 phi n square dx equal to 1. A will be again root 2 by a. So that's how you will normalize. Now there is one more thing, you just need to remember this formula. So energy eigenvalue will remain same both cases, asymmetric and symmetric, and the eigenstates will be for symmetric cases cos for odd, sine for even, and in place of L you just need to put the value of this length. Like it is minus a by 2, then it will be total length will be a, so you just need to put in place of L a. And similarly for the asymmetric cases, whatever the length is, just put the length value here and you will get the equation. So this is the easy trick you can remember very easily. Just substitute the value of L, whatever length is there, and you will get the equation or the eigenstates. Now I will give some question to you at your homework. So in the next lecture I will provide the solution, but first you need to try by yourself, only then it will be helpful in the exams. The wave function of a particle in an infinite deep square well potential from x equal to 0 to a, it is the asymmetric case, and the wave function is given 1 upon root 5 phi 1x plus 2 phi 2x, and phi and phi 2 are eigenstates corresponding to ground and the first excited state. So you know for the ground and the first excited state, that will be this root 2 by a, means these are your first, this is your second. So there, that's how you will substitute it here. In place of phi 1 just write that one, and phi 2 write this one, and in place of a you will write this root 2 by a, and this length is 0 to a, that's why Ls will be a. So you can just put the value of phi 1 and phi 2, you will get your time independent wave function, and that will be this. Now you will have two sine curves, and you can just plot them. And now you need to find a time dependent wave function. So you will just operate the formula I gave you, this one, and you will get the time dependent wave function. So first try to do it by yourself, and there is some more question I will give you. Just write them. Particle in infinite square potential, and the wave function is given under root 30 x a minus x a raised to power 5 by 2, x is 0 to a. Find the probability of finding the energy to be h cut square pi square 2m a square. So you need to solve it by yourself. Find expected value of x and momentum, position and momentum, particle in infinite square potential of x equal to 0 and x equal to a. Prove that the expected value of x square equal to a square 1 upon 3 minus 1 upon 2 n square pi square. Then for the momentum square, it will be n square pi square h square by 2 a square. So try to prove them. Prove del x del p equal to n pi h cut under root 1 upon 12 minus 1 upon 2n square pi square. Find the probability of finding the particle in nth state for symmetric square potential and asymmetric. Then again, the time independent wave function psi x0 equal to a by root a sin pi x by a, and plus root 3 by 5a sin 3 pi x by a plus 1 upon root 5a sin 5x by a. So you need to find the a value and find the expected value of energy. And again, next question is Vx equal to 0 for x0 to a and find it for otherwise. The particle is in the ground state and the size of the potential well is suddenly increased 4 times. While moving RHS, means right hand side wall, from x equal to a to x equal to 4a, this will become 4 times, and where x equal to 0 is fixed. So you need to do what? What is the probability of finding the particle in ground state of new potential well and the first excited state of the new potential well? So you need to find this probability. So actually I covered all kind of questions can be asked from this infinite square potential well. So try to solve them. In the next lecture I will give the solution. So that's it for today. Thank you everyone.